Hello, everybody, and welcome to the February 3rd meeting of Chem 220. So today we're going to continue our discussion about alkenes. But before I get to that, I sent everybody a link earlier today. We start February as African American History Month. And the link that I sent you is a link about a particular man, Dr. Percy Julian. He was instrumental in my success as an organic chemist. There was a time when I was struggling in my research and looking for some answers. And I went back to Dr. Julian's papers from back in the 1950s and 60s. And lo and behold, I found my answers in his science. And his story is much more than about chemistry. Now, that link I sent you is a PBS movie, and it's about an hour and 50 minutes long, so it's not trivial. It would take a while to get through. But if you would watch that film, I will reward you with one question from that movie, which if you watch that film, you can't get it wrong. So people have been asking me about the exam, how many questions, or, so I would say at this point, 25 questions, okay? That would mean for most people, you should be able to finish in about an hour time. So if you, let's say 2 minutes per question, 25 questions, that would be 50 minutes. So the average student should be able to finish in about an hour. Now, some people are much faster and they'll finish ahead of time. Some people might take a little bit longer, and you are certainly welcome to take the full hour and 15 minutes to complete the exam. And remember, if you are a DSO, you take it from, oh, am I freezing? I see somebody says I'm freezing. I live out here in the country, and I have this terrible DSL internet, and it's unfortunately my computer is not all that great. So I might be breaking up a little bit, but hopefully you'll be able to at least get the gist of most of what I'm saying. All right. So if you would, at your leisure, whenever you get a chance, discover Dr. Julian. Most of you have heard of, George Washington Carver and maybe several other very famous African-American scientists. But my guess is you have no clue as to who Dr. Julian is. But since you are all taking organic chemistry, I think it's very important that you should know who Percy Julian was and what kind of a man he was. So again, if you want a free 4 points, 25 questions, that means 4 points per question. On a 100-point exam, there's a free 4 points. The other question that I will ask you, which is again, a freebie, you want another 4 points on your test? One question will come from the syllabus, all right? So just read the syllabus the day of the exam, and I guarantee you, you'll get that question right, okay? So that should be okay. All right, so let us now continue our discussion about the project real quickly. I briefly mentioned the project last class, and what I'd like to do is talk just a little bit more because I've been getting a lot of questions about, I have no idea what I should do or what molecule or molecules. It doesn't have to be a molecule. It can be a class of molecules. But what kind of organic molecule is even plausible? And I started to ask her some questions and, trying to find out, first off, I just wanted to know what her major was. And it turns out she's a nutrition major. And so I talked to her a little bit more about what led her into nutrition. And it turns out that her family owns a restaurant, an Indian restaurant. So I've never been to India, but I love Indian food. And I love the spices of Indian food. I'm getting this message. My internet is unstable. Oh, I hope you're able to see some of this technology. Now, once we go to in class next week, but again, it'll be taped. That Panopto streaming system will tape what happens. So if you can't make it, or if you're not feeling well, definitely don't come to class next week. Just look at the Panopto video, and I'll show you that link maybe next week. It's really easy. It's just like a Zoom. Just think of Panopto like a Zoom on steroids. It's able to capture lots of different screens at the same time. Okay, so the project. So I started to ask her about her family, and she told me about all these spices that go into Indian cooking, whether it be turmeric or cumin, or there's so many different spices. Well, you know what? The organic chemistry of spices is remarkable. The biological implications of these molecules, these organic molecules in spices, is incredible. You could do 50 papers on that. Now, I'm not suggesting everybody go do organic chemistry of spices. This is just one suggestion I had for her, and she seemed receptive to it. I don't know if she will or not. But whether it's like today, we're going to talk about tires and rubbers and all kinds of polymers of alkenes. Maybe you're a materials person. Maybe you're in material science. Now, you need to talk about soft materials in your paper. Materials chemistry could be steel and alloys of steel. Materials chemistry could be ceramics. But none of those things are organic. This is an organic class. So if you're a materials science person, you need to talk about soft materials, polymeric materials. So maybe you're interested in materials as it applies to transportation. Well, petroleum, the different kinds of fuels that we use, alternate petroleum products. There's a whole field, burgeoning field in aviation of using sustainable sources of fuels where they capture CO2 from different sources and they make fuel out of carbon dioxide, and they're running aviation. They're running jets on this stuff. And there have been several pilot programs. Maybe that's what you're into. Maybe you're an ag person and you are fascinated by crop science, and you want to know, how do I prevent crops from pesticide damage, or how do I incorporate natural pesticides into crop rotations? Or maybe I'm interested in biofertilizers. There's a whole burgeoning field of biofertilizers. We don't have to use ammonium nitrate all the time on our crops. We can grow food without having massive amounts of ammonia. There's lots of downsides to using that anyway. It gets into the water, the phosphorus and the nitrogen get into the creeks, the algae blooms happen, and then you get fish die-offs. So, we need to start thinking more broadly about how we use chemicals. And so that's what I want you to do in your field, whatever is interesting to you. And if you want to talk to me about it or email me about it, I am a textile major. What kind of projects do you think maybe would be good for a textile major? Well, email me. I'll send you some suggestions. And again, you don't have to follow me at all. The only thing I would like you to do, though, please, before you actually begin a big wholesale dive into your project, I would like you to email me and just get a quick okay, all right? To make sure that you're not too broad and you're really doing something that's related to organic chemistry. So please do that favor for me. All right, so enough said about the preliminary stuff. We got a lot to do today. Let me go ahead and share my screen and get to our lecture. Okay, so here we go. I got to get my pencil out real quick. All right. So, not this, that's just the cover page. Okay. Now, we have talked in the last class about how to make alkenes, and then a little bit about the physical properties of alkenes. You know, they are hydrocarbons. They're just made of carbon and hydrogen. So they're not very polar, but they're more polar than saturated hydrocarbons, ones that have only single bonds. Now, one thing about alkenes that was really important in the last lecture that you have to make sure that you're aware of is that alkenes, the pi bond of an alkene is very electron rich. And remember, we have pi bonds and we have sigma bonds of a double bond. The sigma bond is the one between the two atoms. The pi bond is that region of overlap above and below the plane of that sigma bond. Now, I have listed several reactions here just for examples that alkenes undergo. I will not ask you to draw any of these. I will not ask you. The only thing about this particular slide that I want you to keep in mind is that alkenes undergo addition reactions. That's one of the reactions they undergo, additions. They add things. They incorporate things. So in this particular case, it was 2 hydrogen atoms, 2 more hydrogens in the product that were not in the starting material. In this reaction, oh, sorry, Br, not B. That's B is boron. Let me erase that. Bromine. There are 2 new bromine atoms that are in the product that were not there in the starting material. In the third example, there's a hydrogen and a bromine that were not in the starting material. And lastly, there's an oxygen. That's called an epoxidation reaction, the bottom one. Now, what I want you to notice in all the reactions, a double bond became a single bond. In every single one of these reactions, where there used to be a double bond in the starting material, there's only a single bond in the product, okay? Now, don't worry about the regiochemistry or even the reactions themselves. I'm not going to ask you to solve any. These are called synthesis problems. Regular full-blown 221, 223 sequence would involve that, but not for us. All right, so that is one of the principal reactions of alkenes. Now let's talk about another reaction, polymerization. Because like I said earlier, the big thing in this class is how does organic chemistry affect you? Well, in terms of these alkenes, the one thing that affects you on a day-to-day basis are the polymers of alkenes. These are the things you interact with every single day. My guess is you are wearing a polymerized product. My guess is you are looking at a screen and a computer and the keys that are made of polymers of alkenes. My guess is the shoes you are wearing right now have polymeric alkenes as part of their makeup. So they're everywhere. And to our great benefit, but as you'll see at the end of class, to our great peril as well. Because the other place that you don't realize there are plastics, polymers of alkenes are called plastics too, by the way. That's another term we use for polymeric alkenes. We call them plastics. And we'll talk about a couple of different types of plastics as we go along. But what you may not realize is circulating in your body right now, you have plastics, you have microplastics, and that is not usually a healthy thing. We'll talk about that later. Let's go ahead and look at polymers of alkenes. All right. So the first one, the simplest one we'll learn, is a cationic polymerization of ethylene. Okay, the alkene, the simplest alkene, 2 carbons and 4 hydrogens. Now let's go through this. 2 alkenes by themselves are not going to react. We need something to start we need to start it off. We need to initiate the polymerization. Now, we have cationic, we have anionic, and we have free radical. So there's 3 different kinds of ways that we can hook up these monomers, and that's what the individual alkenes are called. They are called monomers. Mono, one, mers. They react to form long chains, which we call polymers, poly. Now, in the case of ethylene, we need to start this off with a little bit of acid. That's what the H plus is, cationic. So as I mentioned last class, the pi bond of alkenes is very basic, Lewis basic. So it attacks positive things. And that's this arrow that I show you right here. The pi bond attacking the positive thing. Now, when that pi bond makes a new sigma bond, and here's this new sigma bond out here, that used to be the bond to the other carbon. So look here, that created a positive charge on that carbon when the pi bond reacted with the H plus. Then another alkene negative pi bond attacks the positive carbon. And then again, here's another negativeness of a pi bond attacking this positive, and so on, and so on, and so on, and it makes a long chain. Now, depending upon how long the chain is, we can get low density polyethylene or high density polyethylene. It's just a matter of the molecular weight. How many monomeric units linked up together? And these have different properties. So the low density polyethylene is more like a film, like plastic wrap. The higher density polyethylene is harder, more firm, and it's good for making things like bottles out of. So maybe you have a plastic drinking bottle next to your computer right now. Obviously, don't spill. But that plastic bottle is probably a higher density polyethylene. Milk bottles, you get a gallon of milk, probably a higher density polyethylene. Now look at the compound over here to the left. If I replace the hydrogens of ethylene with all, oh, that should be a fluorine, by the way. I made a mistake there. This should not be a hydrogen. That should be an F. If I take tetrafluoroethylene, and do the same reaction, polymerize tetrafluoroethylene, I make a polymer of tetrafluoroethylene. And this is known as Teflon. Sometimes we coat pans with them. It's a very non-stick surface. And there's a fascinating story about how Teflon was discovered. A man had some tetrafluoroethylene, and he had it in a cylinder, an iron cylinder. And this gas, tetrafluoroethylene, is a gas in this iron cylinder. And then when he opened up the bottle, he noticed that the pressure kept going down. So he put in 100 psi of this gas into this iron bottle. And then he'd come back the next day and the pressure was down to 0. And he thought, well, maybe my valve is leaking. And then he looked at 2 other bottles that also had tetrafluoroethylene gas monomer in the iron bottle. They also had gone from a pressure of 1,000 psi to 0 overnight. Well, this was obviously, it couldn't be just a fluke of nature that all of the valves on his gas cylinders went bad at the same time. So he cut open one of the cylinders and he noticed this white powder fell out of the bottle. That white powder was Teflon. And then he melted the Teflon and he found he couldn't get it to stick to anything. This was a man from DuPont, by the way. And then lo and behold, somebody else came along and says, you can't get it to stick to the flask, you can't get it. Oh, I wonder if we could use that property. And sure enough, then Teflon made DuPont hundreds and hundreds of millions of dollars over the years. And so there's a case of serendipity, right? A case of accidental discovery leading to a multi-billion-dollar product, Teflon. All right. Now, polymers, as you see, could be what we call homopolymers. Homopolymers. What does a homopolymer mean? It has nothing to do with sexuality. It has to do with the repeat units. A homopolymer is made of one kind of monomer. So amylose, starch, is a homopolymer of glucose. Teflon is a homopolymer of tetrafluoroethylene. And all of these down here, these are all homopolymers, polypropylene. Where you see a lot of polypropylene, number 1 there, carpet fibers, boat lines, a lot of that is made of polypropylene. Polystyrene, I think you know what polystyrene is, you know, things like coffee cups and those sorts of things. Polybutylene, we're going to have a lot of talk about polybutylene. As a matter of fact, a combination of polystyrene and polybutylene is called styrene butylene rubber, SBR. Polystyrene polybutylene rubbers. Now, let's think about taking 2 monomers and hooking them together. We can have something called a block copolymer, block copolymer. So the units alternate, AB, 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 till you make this big monomer. Now, styrene butylene rubber that we use for car tires, we'll talk about that in a minute, car tires, is not a block copolymer. It's a heteropolymer in which we have several AAAs and then maybe a couple of BBs and then several AAAs and then several BBBBs, but it's not a defined repeat unit. They don't have a definite repeating rhythm to that polymer. So this will impart different properties, just like PVC, polyvinyl chloride. You know, where do we find PVC? Have you ever seen at Home Depot or Lowe's home store, you see this white pipe? So PVC piping is a lot of times used for applications in home building, and we see that quite a bit. It's very rigid, isn't it? Like if somebody hits you with a piece of PVC, you would know it. It's hard, but you can cut it, you can connect it together, you can use different adhesives that link all the piping together. So that's kind of nice. So that's a good thing. All right, continuing our discussion of alkene polymerization. Let me tell you a story, an important story, a historical story about rubber. Now, obviously, rubber, as you know, latex rubber, was a natural rubber from the rubber plant, the rubber tree. And people would milk, that was the term. I know it's not really milk. It's not like milking a cow. But they would cut open the rubber tree and they put buckets and they would isolate this oozing material from the rubber tree. And then they boil off the water. And what they found was this long polymer of latex. And the monomer that this came from was isoprene. Here's isoprene right here. So it's 2-methyl. So here's 1, 2, 3, 4. And this is a CH3, so that's a methyl group. 2-methyl 1,3-butadiene. You don't ever have to remember that name. You don't ever have to remember the structure. I draw the molecule for you. I give you the name of the molecule. But just like all of these alkene polymers, they form these connections, these long connections, and they make this long straight chain of isoprene, polyisoprene. Now, polyisoprene itself, we do use it. It maybe like in gum erasers or in certain applications, but it's not a rubber that you could use for tire applications. And so, they initially tried, but it didn't stand up very well. But a man came along in the early 1900s, late 1800s, early 1900s, Charles Goodyear. Maybe you've heard of Goodyear tires, right? Maybe you have some Goodyear tires on your car right now, or maybe mom or dad's car. So what Charles Goodyear discovered in trial and error, he was a homeschooled chemist. He taught himself chemistry, but he wanted to discover some way to use these natural rubbers and make them more useful. And he tried lots of things, but he eventually discovered that when he cooked the isoprene polymer, the latex rubber, with sulfur, that cross-linked, the sulfur hooked up the chains and linked them all together, made them much stiffer. This process, by the way, has a name. It's called vulcanization. To vulcanize rubber means to cross-link it, means to take these long individual chains and hook them all together. So this cross-linked polymer then, along with some carbon black, made for the early car tires. And that was very important, especially after World War I, where we didn't have enough latex. You know, when World War II started, a lot of the rubber plants, a lot of the rubber trees, they were from Indonesia, from the Far East. And guess who owned the Far East back in World War II? The Japanese, right? So the Japanese, they had a lock on this latex, but the Americans and the Germans especially were very industrious. So they needed a rubber that was very like this vulcanized latex. They needed to find something that had similar properties. And so they found that another polymer styrene, butylene, rubber polymers had very similar properties to these early latex vulcanized rubbers, and they could be used for car tires. Now, we didn't have to rely on Indonesian rubber plantations that the Japanese controlled. So we, obviously, a lot of Jeeps and other vehicles for the war effort relied on rubber for their tires, and certainly cars in the United States too. So this became our de facto even today. We do not use this old rubber anymore. We don't use latex rubbers in our car tires. We pretty much use SBIR polymers today. Now, SBIR is known as a thermoset. Matter of fact, vulcanized rubber is also a thermoset polymer, as opposed to a thermoplastic polymer. So what is the difference between a thermoset and a thermoplastic? Well, a thermoset, as the name implies, is a polymer that you cannot take back. You cannot reset it. So I can't take old car tires and melt them into the monomer. Now, obviously, car tires are much more than just the rubber itself, right? So, there's also carbon black that's used in car tires. We have belts. We have this stuff underneath the rubber so that makes them less prone to getting punctured. Sometimes these belts are made of metal. So we have iron belted tires, steel belted tires. Some of these belts are made of fibers. So we have these plastics that keep the tire from getting punctured so easily, and also give it a little bit of rigidity as well. Now, those are thermoset polymers. We cannot take them back and make new tires out of old tires in that regard. Now, what we can do with those old tires, we can shred them up and we can mix them with asphalt and we can make new roads out of them. We can take the old tires and make playground equipment out of it. We can shred them up and use that rubber on different, like for mulches, but we can't make new tires out of old tires. We got to use the new virgin SBIR polymer. Now contrast that to thermoplastic polymers. You remember, okay, let me go back. You remember polyethylene, like the bags you get at the grocery store. That's a kind of polyethylene. So there's a downside to that. We'll talk about that at the end of class. But the polyethylene, then, we can go ahead and make new bags out of old bags. I can melt an old bag from that material and make a new bag out of the old bag. That's called thermoplastics. So obviously, thermoplastics are very friendly for recycling. Thermoset polymers are not. And so, a lot of times, it's very good to recycle when you can, because then we can make new products out of the old products. And we'll see how that will work here in just a moment. All right, so here is that SBR polymer. Wow, look at how complicated this is. So this is styrene right here. Styrene is a aromatic ring. Remember we talked about aromatic rings, has to be in a ring. It has to have alternating double and single bonds, like the benzene ring. There's a benzene ring right there. Carbon, double bond carbon, single bond carbon, double bond carbon, all the way around. So there's the styrene. And what styrene has is a double bond right here. Now, if we hook that up to butylene, here's a butylene right here. So here's a styrene monomer hooked together with 1,3-butadiene. Then this 1,3-butadiene is hooked up to this styrene. Then this styrene is hooked up to this butadiene. Now look over here. Now here's where it breaks apart. I got two styrenes hooked right next to each other, don't I? So this is not a block copolymer. It doesn't have that repeat. It's not an AB, 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 AB. This is an A, B, A, B, A, and then, whatever this N just means, this repeats itself. So this is going out infinitum out here, infinitum there. Now, a lot of the SBI polymers are not done by cationic means. They're done by radical polymerizations. So here's just an alkene that I make radicals out of. So here's the pi bond right here. One electron goes to this carbon. The other electron goes to this carbon. Wow, look at that. Where have we seen this before? Remember in last class when we talked about fission, where the pi bond makes two radicals. Then this was locked. So right here, locked. No free rotation. Free rotation. Once it's a single bond, it can spin. It can freely rotate. Now, these things can hook up one to another. So here's one diradical. Here's another radical. This radical hooks up to this radical. And now we've made this new chemical bond, right from there to there. Here's my new bond, which came from the two radicals. Then this can hook up with another one. This can hook up with another one, and so on and so on and so on to make our SBIR polymer. And again, if you're going to make a car tire out of it, you're certainly going to add things like carbon black. Maybe you're going to add some steel belts to it. You're going to add a whole bunch of other additives to the car tire. So car tires in general are not really, obviously they're incredibly important to us, but they're not very environmentally friendly in terms of what we can do with them afterward. And obviously, car tires after they wear out, what happens to all that rubber, that's off on the side of the road, it goes off into the grass. I have no idea, but my guess is it's not very healthy for the environment. Okay. Now, let's talk about plastics in general, not just car tires, but just plastics in general. So what are some of the downsides of using plastics? Well, obviously they've created a lot of important consumer goods for us, but when we get rid of them, they create a challenge. And here's just one of many challenges. This is called the Great Pacific Garbage Patch. This is a patch of plastics. Here's California. Here's the United States out here. Here's Alaska. Here's Japan, Asia. So you see there's a current, a Pacific current, comes across from Japan, comes over, circulates across California, comes off the southern coast of California and Mexico, and then works its way back across the Pacific Ocean to Southeast Asia. So here's New Zealand and Australia are down here. Well, what this creates is this vortex. And right in the middle of this vortex is this massive, massive area of plastic waste. You'll have to, let me see if I can make this big. This gives you an example of this. So this area over here in the square, this Hawaiian archipelago, we're gonna look at that in a closer area down here. This is obviously not to scale. So it's just kind of showing you off the coast of California is this area in the middle of the Pacific Ocean. And they have modeled the concentration of plastics, the kilograms of plastics per kilometer of space. And you see here, look at this, 101, this huge area of circulating plastics. Well, guess what else is in the Pacific Ocean? Turtles, whales, fish, dolphins, all kinds of wildlife that are impacted by this mass of plastics in the Pacific Ocean. Now, if they're very large pieces of plastic, let's say we've got some fishing nets in here. Or we've got some bottle caps. Well, what happens to a turtle when it gets hung up in the fishing net? It's going to die. What happens to the whale when he ingests or she ingests? I guess whales come in both sexes, of course. Otherwise, we won't have more whales if we don't have them both. What happens when the whales ingest all this plastic? They get very sick and they die. The turtles ingest it, they die. So it is in our best interest to keep this plastic out of the environment. And this plastic is everything, by the way. It's the plastic bags from the supermarket. It's the plastic bottle rings from the soda cans. It's the plastic from the boat operations. And as later on, we're going to see the plastics from even textiles and clothing end up in this garbage waste. So what do? Well, there's a lot of people trying to do at least something. Now, obviously, what I'm going to talk about now is a minimal contribution, but let me make this small here, bring this up a little bit. So there are companies now that can take these plastic bottles and they can shred them up into these flakes. Now, these obviously have to be thermoplastic polymers. This won't work on thermoset polymers. It's got to be a thermoplastic. So if you take the plastic flake and you melt it, and you take this melted plastic and you extrude it, extrusion, that's a fancy way to say I'm going to push it through a little hole. That's what extrusion is. I'm going to take this melted plastic, I'm going to push it through this tiny little hole, and that melted plastic is going to spin out and cool off. Well, that's going to make yarn. And we could take this extruded yarn and we can make stuff out of it. We can make shirts. We can make performance wear. I have a lot of running shirts that I use that are from old plastic bottles. So if you want to help the environment and do good work, there are a lot of companies that you can get online. So just go to Google and put in plastic bottle shirts, and you'll come up with a whole bunch of companies that make shirts out of old plastic, and pants and other kinds of performance wear out of these old bottles. So that's one bottle that didn't find its way into the Pacific garbage. But again, you can't throw your old shirt away. You got to recycle the old shirt too. And again, since this is the same polymer, we can recycle these old plastic shirts and make new shirts out of the old shirts. And by the way, these shirts are great. They're very wicking. They take a lot of moisture away from you. So if you're working out, these are good shirts to work out in. They're very soft, buttery soft. They're wonderful, wonderful shirts. So I recommend you try to start learning about how people are recycling plastics into other useful consumer goods. Okay, continuing on. Now let's talk about a different problem. Microplastics. What is a microplastic? Well, many years ago, a scientist who was studying plastics in the environment, he defined microplastics as anything less than 5 millimeters in size. It's pretty small, pretty tiny. But a lot of microplastics are much, much smaller than that. And these microplastics can be very damaging. So first off, where do we find these where do these microplastics come from? Well, some are made by design. The cosmetics industry uses a lot of microplastics in scrubs, exfoliants. So, a lot of ladies will scrub their face to get rid of their makeup. That's kind of sexist, isn't it? I guess boys can wear makeup too. I take it back. Don't write any letters to the dean that I'm being sexist. So exfoliants to take off surface grime. Let's just do it that way. Whether it be sweat or suntan lotion or makeup, a lot of these scrubs, these facial scrubs, have microbeads. in them. Some of them even advertise, we have microbead scrub. And they are kind of nice because they do get rid of a lot of stuff off your face, which is good. Sometimes I steal my wife's. Now, also the paint industry uses a lot of microplastics to get rid of surface grime and paint. So whether it be oil on a surface of a metal or paint on a boat hull, you know, we can use sand. Sand has been traditionally used to blast away paint and to blast away oil off of machine parts, but also so too are small little microbeads of plastic used to blast away these materials, okay? So we call these primary microplastics. Remember that little 1 degree sign when we talked about carbon atoms? That's the symbol for primary. 1 degree means primary. So these are particular microplastics that are made at that very tiny level, primary microplastics. Another source of microplastics comes from the breakdown of larger plastics, the plastic bags, the boat cooler that you accidentally fell out of the boat and ended up in the ocean that ended up degrading. Well, what happens is those larger plastics in light radiation can get broken apart and make these smaller pieces of plastic, microplastics. We talked about car and truck tires running down the road, right? So as the friction, as the car is rolling down the road, tiny, tiny little pieces of rubber are left on the road. Now, I'm not talking about idiots that burn out or you know, or do stupid things like that. What a waste of good tires. I'm talking about people just normally driving down the road. Some of that rubber is going to come off of your tire and end up in the side of the road, and that water from the rain is going to wash the rubber from the tires down to the creek. The creek's going to end up in the river. The river is going to end up in the ocean. So all of a sudden, what happened to all that rubber from the tires? It's out in the ocean, or it's in the creek, or it's in your body, as we'll discover in a minute. Now, we talked about fishing nets, obviously. Fishing nets are a big problem. They can break off from the boats and cause problems when they're large, but also the microplastics from the fishing nets, the polypropylene fishing nets, can break apart and cause all kinds of problems. Plastic grocery bags. Why do a lot of communities now outlaw plastic grocery bags? Because of the microplastics, this accumulation of plastic in our environment. Packaging. What have you bought recently that didn't come wrapped in some kind of plastic? Plastic straws. I never ask for a plastic straw. Matter of fact, if the waiter or waitress gives me a plastic straw and I have a cup of water in front of me, I say, no, thank you. And I hand it back to her or him. You should do the same thing. We don't need all these plastic straws going into the landfill, which then create microplastics. Because eventually, this is going to lead to biological accumulation in all living things. If I analyze your blood right now, if I take a sample of your blood, I will find microplastics in your blood. It's in the placenta of women who are pregnant. It's everywhere. And we don't know all the implications of what happens to our bodies as we start accumulating all this plastic. Maybe it's just benign. Maybe nothing happens and we just bioaccumulate it because, you know, it may stick with us a long time. We're not going to assimilate a lot of these plastics. So that can be very dangerous. All right. So with that, I want to pause and stop for a minute, and I'm going to give you an opportunity to pull up your Kahoot. So let me stop my share, and I want to do a Kahoot now. Let me stop that share and bring up, you can go ahead and pull up your Kahoot program. See if I can find Find my internet. Go back down. I had it up earlier. May have to bring it back up again. Let me see if I can find it. I think it may have timed myself out. Okay, let me bring up Kahoot again one more time. Okay, it's coming. Okay, here we go. Share screen. Make mine a little bit bigger. All right, so I'll give everybody a few more minutes. I'll go ahead and I'll play the game, but I won't start it yet. I'll just start play, and then that'll still give you an opportunity. And remember, if you could use your Kahoot number, not your name, would be better. So the number that you're going to put into Kahoot, hold on a sec. Boy, my internet is so bad. I'm so sorry. It's tough living out in the country. Okay, let's do classic mode. Number will be here in a second. Okay, if you would put in 473 797. 473 797. Maybe another 2 more minutes or so. We will begin our Kahoot. Okay. Go ahead and start our Kahoot because it seems like we've reached sort of a plateau here with participants. And also I've added more time. Okay, modern automobile tires are made with this particular polymer. Let's see if I can increase that up a little bit. Polyethylene, PVC, SBIR, or Teflon. So there you got a bunch of tires up there. I hope you don't have to get new tires anytime soon. I just put on some new tires on my car. Oh, that was expensive. Can't believe how expensive tires are. Give you a hint, it's not a homopolymer. It's a heteropolymer. It is SBIR. Very good. Most of you got that correct. Styrene butadiene rubbers. So styrene butadiene rubbers we find in most modern tires and bicycle tires and other products too. But that's the dominant one that we use now. All right, let's go on. Well done. Second question. This person was responsible for the vulcanization process. Who invented vulcanization? Oh, for some reason, this is a much longer one. Sorry about the timing here. I messed that up. Hopefully people were able to get that. I think I had to, I changed the time on the first question, but I think I have to do it for every individual question. There was a concern that the time was coming up and down really fast. And so I added the first question to be 1 full minute, but I think the subsequent questions have not been changed. So you might have to be kind of quick on the ball here, and I'll fix that on the next Kahoot session that we have. I'll do that one really quickly. Well, I'll do it. I don't know if I can do it midstream here. Let's just continue because I don't want to mess up the game or the Kahoot questioning. But next time, each question will be a full minute long. But my guess is the rest of these questions are going to be maybe 20 or 30 seconds. So you're going to have to be kind of fast on the ball. Okay. Pi bonds of alkenes are they electron rich, electron poor, ionic, or neutral? And again, I'm sorry about that. That question's only 20 seconds long. That was bad. I'll repair that next time. Electron rich. Good job. You're all paying attention. Very good. So that pi bond is very electron rich. It's going to go out and attack positive things. Remember what we called that? Lewis base, Lewis acid. The pi bond of the alkene is Lewis basic. Whatever it's attacking, maybe it's a proton, that's a Lewis acid. Okay, well done. Good job. And I guess all of these are going to be 20 seconds. So the rest of these are going to be 20 seconds instead of a full minute. But next time I make a Kahoot, all of them will be a full minute. All right, next one, here we go. True or false? Thermoplastic polymers can be melted and reformed. Helpful for recycling. Thermoplastic. Think of plastic bags that you take back to the grocery store. I hope that's what you do with them. Don't throw them in the trash. That is true. You can take thermoplastics, you can melt them and recast them. Milk bottles, that's an example of a thermoplastic. So you took the bottle, you shredded it up, you melted it, you heated that polymer up, that polymer became a liquid, and then you pushed that liquid melted polymer through a tiny little hole. That's called extrusion. And that made a fiber. And then you could take that fiber and you could make t-shirts out of it or other materials out of it. So very important that we recycle our thermoplastic polymers. Continuing. Vulcanization. Cross-linking polymers use what material? Phosphorus, chlorine, silicon, or sulfur? What will cross-link polymers? What element will cross-link the polymers? What did George Goodyear use to make his tires? Sulfur, that's right. Sulfur is the cross-linking material that will allow the chains to form a much more rigid polymer, because we don't want the tires to be, well, they have to be somewhat flexible, right? So if you hit a pothole, you don't want to damage your rims, so you need that tire to flex, because if the rubber is too hard, that's very harsh. So things like truck tires, like 18-wheelers, their tires are very, very, very high pressure and are made of a very, very hard rubber. So truck tires, big 18-wheeler truck tires, the kind of rubber that they make is extremely hard. Now, what advantage does that have? Well, here's one advantage. A truck tire can go 100,000 miles on a truck tire before you have to replace them. Now, you're not going to get probably 100,000 miles on a car tire. I seriously doubt it. You're lucky if you get 40,000 miles, 50,000 miles out of your car tires. So the harder the tire, the harsher the ride, higher the pressure that you can put in it. Remember, high pressure is good for rolling resistance, right? So if you put a lot of pressure in your tire, it's easier for that tire to roll. Just imagine your bike tires being low pressure, kind of hard to pedal, isn't it? Same thing in a truck tire. High pressure, very hard, lots of miles, but at a cost of ride. All right, so that is it for our Kahoot. I will stop my share here in just a second. Where is it? Here we go. Stop share. All right. So we're back. Let me turn my speaker up just a little bit. And I'm going to get out of this Kahoot because that music is crazy. Go back to my Zoom. And we have about 10 minutes or so. If anybody needs to ask any questions, again, I am planning on it, and I'm pretty sure this will happen. So this coming Monday, not Monday, this coming Tuesday, I'm going to be in Dabney 222. So, and again, if you can't make it, it's going to be recorded, just like we're recording right now. So if you're not feeling well, please don't come. Or if you got some other appointment, just watch the lecture later. But we will gather together, finally, at last. We will gather in class on campus. Kind of excited. Now, again, I'm going to look at the numbers one more time on Sunday. I'm going to get on the dashboard, the NCSU COVID dashboard. And if I see a spike, then I may have to call off Tuesday. But I'm not anticipating that. And several of the physicians have told me that all the trends are in the right direction. So they are not anticipating anything going up, but actually in the opposite direction, things moving downward. So let's just keep our fingers crossed that we will finally be able to get together on Tuesday of next week. Okay, anybody got any questions?
Hi, Dr. Brown. I know we were
Yep.
playing the Kahoot and we had Kahoot numbers.
Yeah.
I was wondering when you gave those out, I really missed it, or if it's online.
The Kahoot, like next week, you mean on Tuesday?
Oh no, I just meant like the kind of like game numbers, like 100, 428 PB. Like when were
Okay,
we?
yeah, your Kahoot number. Yeah. You don't have one?
I'm sure you gave me one, but maybe I wasn't there, or is it online and I like go to a document where it's posted online?
Yeah, I had sent those out as part of an email file, but for students who added the class late, you probably were not assigned a Kahoot number. So if you don't have a Kahoot number, just email me and I will go to my list. And if you're not there, I'll add you to the Kahoot roster. And then I will assign you a Kahoot number. So if you don't have one, please email me and I will get you a Kahoot number and you can have that going forward.
Thank you so much. I really appreciate it.
No worries at all. Anybody else? Yeah.
I had a quick question.
Sure.
The Kahoots.
Yeah.
In the syllabus, we need only 75% of them to get 100, correct?
That's right. So you could miss one out of every 4 and you'll have 100 grade.
Yeah, because like
And that's homework too. Homework is the same way, by the way.
Like
so
this
if you,
Kahoot, my answers, most of them didn't even go through because I have such a delay. I don't know if there's a lag or something going on.
yeah, that's going to go away because the next Kahoot. Do you remember the first question we did today? the times was 60 seconds. I
Yeah.
thought that I was setting all of them to be 60 seconds. But it turns out after we started the quiz, it was only that first question that was 60 seconds. So I actually have to change the default time on every Kahoot question to make them 60 seconds, which I will do in the next Kahoot. So you'll have a full minute time, and it won't matter if you got a little delay or anything else. It'll be a full 60 seconds instead of 20 seconds. So just think about having 3 times the amount of time to answer each question.
All right. Yeah. Cause I just got worried. I'm like, dang, because I got all of them wrong. I'm like, this is going to kill my
No, don't
grade.
worry. Don't worry. There are so many more homework and Kahoot points out there. We haven't even scratched the surface yet. So, if you miss a few here or there, remember, if you can just get to that 75% of whatever the total is, your grade is perfect. You've got all the Kahoot points or all the homework points. So missing a few here or there, or it's trivial, it's irrelevant. Somebody asked me a question though, which I thought was valid. Well, what if I get more than 75%? Do I get extra points? No. The 75 is my buffer. It's designed so that if you happen to miss a few or the computer locked up on you, I don't want all those little hiccups to affect the grade. I want everybody to get all the homework. I want everybody to get all the Kahoots. So that's why I set the threshold to be 75%. So just get to that 75 and you got a perfect homework grade, you got a perfect Kahoot grade. And by the way, it's the same thing for the exams. If you miss an exam for some reason, like all of a sudden you wake up the morning of the test and you got a terrible fever. Oh no, I think I got the COVID. Don't worry about it. Stay in bed. Don't come to class. Don't get everybody sick. Because what I'll do is I'll take whatever score you get on the final exam and I'll put it in the missing test. So that's nice. So you'll have that ability. All right. Everybody looking good? Okay.
Yeah,
Well, yeah,
I have
go
a
ahead.
question.
Sure.
So the lecture will be recorded. Will it be live streamed as well?
Yeah.
when we're in
Live
person?
streamed. Yeah. Live streamed as well. Correct.
Will that be through Zoom or Panopto?
Panopto. Well, I could
Okay.
do both. I can open up a Zoom class too. And then,
Okay.
it's kind of redundant though.
I don't
Because
think
what-
I've ever used a Panopto for like a live stream. I've only watched recordings on that.
Only watched recordings.
Yeah.
That brings up a point. I've never used Panopto, so I'm not sure if it is live streamed or not. But I will find that out, obviously, before next week.
Okay.
And if it's not live recorded, I'll just open up a Zoom meeting so that you could be there just like we're doing now. But instead of seeing my curtains back there, you'll see a blackboard.
Okay, thank you.
You're welcome. Has anybody had a Panopto that was live streamed? Did you ever taken a class with Panopto?
Yeah, it can live stream.
Okay, live stream. Okay, good. Excellent. Okay, good. I'm glad to hear that. The nice thing about that, I can't do any demos here. The thing I hate about being in this room right here is I can't do any demos because I don't have any equipment, and some chemistry is kind of fun to see. I would have loved to have done some reactions with the carbons for you, like burn some fuels. Let you see what the different fuels look like when they're burning. Yeah, so yeah, hopefully when we get on the Panopto, I'll do some demos for you. We'll actually do some chemistry, and you can see some chemistry there too. That'll be fun. I miss doing demos. Okay. Everybody good? Okay, now I will be doing a homework 4. It will be up on Saturday night and it will be due on Wednesday. Okay, so homework number 4 is coming up. I know you're still probably in the midst of homework 3, but you know, we'll do that. Okay, so we'll go ahead and that. It seems like some people like the Zoom better than the Panopto. I'm getting some chats here. Maybe I'll just do them both so that you'll have then you could choose whichever one you like. Some people say the Zoom screens are much better and easier to see than the Panopto. Like I say, I've never used Panopto before. It's brand new to me. And I retired back last July. So they didn't even have Panopto when I was teaching. So be a learning experience for all of us. So Tuesday could be a disaster. We'll see. Okay, then. Well, I wish you all a good weekend. Be safe. Socially distance, although I think that's less of an issue lately. And I hope you have a relaxing weekend. Olympics have begun, or not yet, but they are starting, I think, tonight. So I don't know if you're an Olympics fan. I love the Olympics coming up. So don't neglect your studies to watch Olympics. So, but if you want a little downtime, watch some snowboarding and skating, whatever like. It's going to be great. Hasta luego. A todos.
Thank you.